Good morning, everybody. Paul and I will work with our team, our management team at ARM, and we would like to give you an overview where we are with the energy aware scheduling. This topic has been around with us like for years now. We have implementation Android, and the wish is to get this finally into Linux kernel mainline. So the maintenance burden in Android will be smaller than what we have to deal with today. The agenda is I will just give a very brief overview, introduction in what actually EAS is to us right now. We already heard yesterday about, for instance, Quentin, etc. So there are like different components which make energy aware scheduling for us and also for our customers at Google appealing in their products. Then Quentin will give a small technical introduction into how EAS should work in the mainline CFS scheduler. And the biggest part of this presentation should be a discussion about open points we already figured out on the mailing list when we sent out the latest and greatest EAS patch set. And we identified a couple of issues we would like to discuss with you. Introduction. So, energy aware scheduling. What we discussed today is like point number one. That's the energy model, which is the data structure which is behind the energy aware scheduling, which actually enables energy aware scheduling in the wake-up part of CFS. There are other parts of it which essentially make the whole thing work for us, which is frequency and CPU invariance. And the invariance is implemented like we also discussed yesterday already in CFS or in the Perret load tracking system. What's missing is, or what was missing for us is like the engine will actually drive this information. We heard about yesterday about A-curve, M-curve on x86. We heard about activity monitors which might come in future ARM architectures. This implementation we have right now in 4.15 is based on interaction with CPU-free. So you can say that this is like the first step towards making those signals of the load tracking better suitable for wake up, for task placement in the wake up. We have a problem which was worked on by Vincent to update blocked health signals, especially the utilization signals. This patch that might go into 17 as well. UTLS was a topic also yesterday, also Q4 17. What's missing is what Patrick essentially said yesterday, the Quentin facility to be able to allow user space to do a kind of quality of service for the task and not only rely on the natural utilization signals of the task and the CPUs. We have the listed task patch set on LKML in V2 right now, mostly driven by Morton. This is a way like energy aware scheduling. When we do this, we essentially disable load balance completely. But sometimes it's unavoidable that, for instance, a big task with a high utilization value ends up on a small CPU. And this is like a feature which tries to correct those wrong decisions we had to do in wake up. And last but not least, it was also a topic yesterday already. We don't have an architectural feature to detect that an ARM64 architecture, for instance, is a big little system. So we rely on a relatively complex code after the CPU freak system came up to set those flags accordingly on the shed domains, so that the scheduler actually can identify a system as a big little one using this asymmetric CPU capacity shed domain flag. This feature is not actually on LKML right now, but we use it already in certain versions of Android. It's based on a driver we share between ARM and ARM64, the ARC topology driver, which allows us to interact with the scheduler after the CPU system came up. So all those 7 points, if we get this into mainline, I think Google and our other customers using Android might be happy to just go away from the main of simplified kernel releases. People who are essentially aware of what we do so far and also in the Android kernels, they know that we have initially introduced the energy model as a data structure which we introduced per shared domain. And on ARM systems with mostly 2 clusters, we have active and idle energy on per CPU, but also per cluster level. And going forward in mainline, we would like to abandon this idea and just focus on the per CPU data. And we think it's better because it actually allows us to introduce this code much easier into mainline, but also tests over the last couple of years on talks have shown that we can probably neglect the cluster active energy. Another thing we have problems with is to forecast idle states correctly so that we can take idle energy into account in a way that it actually makes sense for the EAS algorithm. Another thing is like we have seen yesterday that we have on different systems we have more than just the MC and die level, but we never really figured out how we can introduce EAS on the SMT layer or on the shared domain layers above die. Taking the ARM architecture further, we have now to deal with also systems which are beyond big little, which are called ARM dynamic. They allow to mix and match different cores with different CPU capacities into one cluster, or what we call a cluster. And so the feature which we have to give up is like that those shared domains spanning different CPUs are also congruent with the frequency domains, which makes the per shared domain energy model more complicated to deal with or to actually make sense of all of this. And with the patch that we sent out a couple of weeks ago, we thought that we have a nice feature identified with the PMOPP library to feed this information from the architecture into the scheduler. But this turned out to be not the case, so and this is one of the discussion points we want to have today.
Maybe just for the first point, to say that cluster active energy almost negligible on models. What do you mean models? So big little legacy, dynamic?
When we started with the energy model, we had the TC2 available, which is ARM system. Yeah. And on this platform, when we measured energy, so we essentially just measured energy for one cluster, we saw like the contribution of the cluster was pretty high comparing to those CPUs. But when we actually deployed these systems on socks like Pixel 2, etc., the benefit was getting smaller and smaller to have a dedicated cluster energy value for active. And that's why this is one point where we thought that the per CPU energy model might be sufficient even for products for the next generation of products.
Also for dynamic systems, not clusters per se, but if you have the island like have 4 little CPUs and 4 DCPUs inside one raster cache, and they are answering like cluster costs in this case, cold cluster costs, and today just like this is not cheaper. So for those architectures, it's not massive. It's not a massive professional taking cost. And the other thing, well, this has to be also seen together with the second point, right? That usually, when you have a big little system, the difference in energy between big and little CPU is more important than like the cost of going on off the cluster. It's usually the case, not always. In practice, we run a lot of tests. We all got just across and these are different high teens, something like that. What we saw is that having a cluster.
I think if you look in the DT, the TC2 for June.
Yeah.
At least for TC2, where we started developing this thing, powering on cluster was way more expensive than powering on the core. I think the cluster might be 5 times as expensive as the core. So you pay 5x to power on the first CPU and 1x to power on the next one. Whereas on the socket that actually shipping the product now, if you dig into the details, I think you'll find that powering on the cluster is maybe half or a third of the cost of powering on a core. So the overhead powering up the cluster is quite small today compared to what it was for that test chip we developed against. So that's why the impact isn't really great. It simplifies things a lot.
I mean, it just gives an idea. I'm fine with having a simple EAS implementation. It's just that I was a bit surprised that the cluster where you have the L3 cache, not dynamic, or you have all the cache for big little, there is a negligible impact that might work. I can understand that the impact is quite small and maybe not worse as the first stage, but the negligible point that for me was
I mean, of course, it will have some effect in some cases, but we found that in practice, it made no difference. That's why we thought it's not worth having a complex energy model that doesn't fit with all the existing stuff.
I mean, I agree that maybe it's not worth the complexity.
Yeah, you have to work hard to come up with a scenario where it actually makes a huge difference.
Particular domain of the project dynamics. Possible to do with dynamics. That can happen in 3D. Three dynamics. Not a dynamic. Happen with 3
Well, it doesn't actually
It's going to actually happen.
You're talking about IP 620.
And there are other ones.
But the 620 had 2 frequency domains.
Not a dynamic.
Yeah, you're right.
It's not a dynamic.
True. But we might see it more often than dynamic system because
Not really. Put it this way, the issue is that voltage cost a lot of money. And actually, complexity has to be.
But okay.
And what happened was, the big little is premium feature. Premium associated people. Big little is now tick box marketing feature, and people will do it. We've had conversations with silicon vendors where you can put a voltage domain down for everyone these domains, and they turn around and say, we're going to put 3 voltages in the whole chip. Anything. Instead of right. They have a very small integer number of volts domains now. And so that has nothing to do with doing that.
The only thing is, if we, like, for instance, have now clusters where we mix CPUs with different CPU capacity, we probably have to require that CPUs with the same CPU capacity, they are in the same frequency domain. So that means, even though from a schedule perspective, you see 8 CPUs in one MC cluster, you will have 3 or 2 domains.
Just to clarify, I'm saying there have been big metals that, like different microarchitectures.
Single voltage domain.
So how is that being?
Okay, but the 620 is not English.
No, but people have done that. You know.
Yeah, but in this case, it's less worried because you have. I think the main point was that you previously want to be sure that you have a level where you can make it. Even if they are sharing the same capacity level at the wider domain. But with dynamic, you can have the opposite to have some difference, so not reflected at any level.
No, I agree with that. I'm just saying.
Yeah.
But it's not an actual thing as much.
Okay. Just before going into the discussion and like addressing all the different issues we identified for EAS, I just wanted to make sure that we all aware what NSUR scheduling really is and just try to briefly explain or re-explain with an example of what we actually intend to do in the scheduler with EAS. So this is well, an example of like typical 4+4 big little system, right? We have 4 little CPUs, 4 big CPUs. The scale here is the capacity of the CPU. and the size of the bar is the utilization, the current utilization of the CPU. And in this example, we have so two frequency domains, one voice cluster, typical case, and I'm under the assumption that we use schedule, and this is why there is well, it's a very simple relation between the OPP that is being selected in a frequency domain and the max utilization of the CPU in that frequency. The question is, we have a new task that's waiting out, that blue task here, that has some utilization, and the scheduler has to make a decision. This task is waking up, the scheduler has to make a decision where to execute these tasks. And this is where EAS comes into play. The idea is that well, EAS is built around an energy model, and the goal is to let the scheduler ask questions to this energy model to say, well, what happens from an energy standpoint if I place that task on CPU1, for example, right? So if this task is waking up, it means that it was running before, so its utilization is actually somewhere in the system. It has a pref CPU, which is CPU 0. And now the scheduler can ask, well, if I place my task on CPU1, what's happened? What happens from an energy standpoint? And what the energy model will do is basically see, well, if you migrate that task, the utilization will move on that CPU, reduce the max utilization in that frequency domain, lower the OPP. And based on this, we can forecast that we are going to reach these OPP if we know how much power is being consumed by CPUs in that frequency domain at that specific OPP. Then we can compute the energy consumed by CPUs inside that frequency. And then the scheduler can ask, well, what happens if I place my task on the other side? And then, depending on the energy efficiency of this OPP versus the energy efficiency of this OPP, the cost of running that task will have different impact on the system energy. And based on this, the scheduler can adjust like the decisions to make it one as well. That's really the base of it. So we'll really discuss how we decided to simplify the energy model. So we have now just per OPP, per CPU data structure. One of the things worth mentioning, in my opinion, is also that there is another subsystem in the kernel that already uses an energy model like that, and that's the thermal subsystem. So there is, yes.
One question with the previous slide.
Yes.
Do you also account for the idle state?
No,
so it will not prefer CPU2 over CPU1 replacement because it will.
Well, actually, so that's one of the things I will intend to discuss later in the presentation. But from an energy standpoint, if the task fits here or here, we can't make a difference from an energy standpoint. It's just the same, right? If you assume that, well, the energy, this is really coefficient, right? We have like a power consumed per unit of utilization, kind of. So putting it here or here from an energy standpoint makes no difference.
Okay, so you don't have a switch on.
So what we are doing with the algorithm right now is, in that case, we usually prefer the CPU that has the max spare capacity. So it's kind of just have spreading what we pack in the cluster to be spread inside the cluster.
So you are saying that from the energy model point of view, you don't have any difference?
Yes, exactly. Because
Just from reality, there is a difference.
Yes, there is one.
Because I assume that CPU1 can be power gated, so irrespective of.
Yes, well,
But the point is to say that it's not worth the difference.
The problem is that you can really predict, right? Because the information you get from the idle state is not really usable, so you don't actually know. I mean, if you were knowing if you could, there will be actually used.
Supposedly, any idle state is better than an active state, right?
Right. So there's always problem,
well.
right?
Yeah. You hope. Yeah.
But in this case, and for most stuff, I mean, if the CPU is only 30% utilized, the deepest per core state. So it's the deepest per core state happen both CPUs, right?
And if you don't pack everything on one CPU,
Well, yeah, that's the other argument.
you can hope that if it does have the right alignment, then you can go cluster alignment. So if you have one CPU and you pack everything, then you cluster and then go.
I'm not sure that works because you can have 30% utilization on 4 CPUs and never reach cluster idle.
Yes, but if you have so that can happen, but it is possible as well. And if you have 100% utilization on one CPU, you are sure that you will never go idle.
And for latency, it is better to case on the other.
Yes, because we should remember there is a performance side of the story as well. So going for optimizing for the potential that could save a little bit of energy at the cost of might not be possible. And as you're saying, it's impossible to predict what the idle state will be. I mean, we had all this information we have all of it in the Android code line, on all the Android code. What we see is that in practice, it doesn't make a lot of difference.
In fact, in the Android line, we have control that says either spread or pack as a hint. For some tasks, we would tend to choose two.
Have additional information.
We have some that say that we're basically saying care more about latency here.
This is outside the
That's outside. Yeah, this is right now in Android. It's not part of any of the proposals.
And so this decision would vary between the cluster you're considering. For example, using the idle CPUs aggressively in the little cluster may not have much effect, but if you are in a big cluster, it may have a different effect. Because usually big cluster, if you have a larger OPP, right? So you better want to use one CPU or like two CPUs instead of spreading all of them and recommend. What you said, the spreading versus packing. So the policy may vary between the CPU, I mean the microarchitecture.
Well, that's as long as the CPUs can be power gated individually, right? Because then if they can't.
Yeah. I think the point is that does it worth the complexity of the algorithm compared to what we are saving, right? That's the point for you.
Yes.
I mean, your assumption is that in order to keep the algorithm simple, you don't want to take that into account.
And also,
which can make sense.
The pressure is basically driven by data you collected, right? I mean, you're comparing the full energy model with this simplification.
If on high density you try like the energy model has cluster cost, idle cost, and everything, and I try like lots of different configurations. So with the idle cost, but just at CPU level, so no idle cost, but actually cost the cluster, and like all these things. And it happens that all of those models, actually none of them is actually like building a better task placement than the simplest one. You just have active things.
Okay, so that's a good argument.
Yeah. For the workloads we care about, and for the work platform effects which are high density.
I'm pretty sure that you can see then it's just a matter of the weight between the complexity and how much you want to save.
Yeah, exactly.
Right.
And how simple you want to stay.
But we based all this on all the workloads we consider realistic and representative of what's happening. Because you can defeat anything with a made-up scenario. Yes.
So, well, so but in any case, starting with a simpler algorithm is better, and then adding more complexity to it and doing the other way around, because you end up.
That was where we started with the first version. Trying to start with what we think is the thing that makes sense. Because we designed this thing based on TC2, where the cluster contributions were huge. That makes sense to have back then, but that was a test chip that's implemented differently than all the products that are now on the market. So,
yeah, so and there are also other arguments to go for this thing. Like we have, so I was going to say, we have the thermal system has it computes the power, the intelligent power allocator, which is one of the thermal governors, computes also an energy model of the platform, which is exactly what we kind of need. So it's a per OPP power estimation. So IPA computes the power of the CPUs as C square F, where C is the capacitance of the CPU, and then F on the voltage or frequency of the OPP at which the CPU is running. And if you compare this energy model with what we have on the IPA Android, which is a measure of things which is really close. So that means that we have already somewhere in the kernel in mainline something that's actually quite good for us. It's probably something we can just leverage and basically agree to.
But we can go this pathway now because we only consider active
Yes.
energy, right?
Yeah.
Before the energy model was much more complicated. So the idle cost we could not get from there or the cluster contribution. But if we essentially get rid of it, we can reuse this.
Yeah.
And it also makes the, like for our customers, easier to create an energy. Because this was like a big step and a problem for a lot of customers.
And another thing, so Charles mentioned SCMI yesterday, and actually the protocol can give you also well
It's designed so that it would.
Yeah.
Funnily enough,
So
it's designed to do.
we don't have idle certificate like that, but we do have those active costs. It's also pretty pricey.
That was the idea, to be able to build it on the product.
So the plan is to unify those.
Yes, so unifying those things, there is already some discussion going on in the list in order to do that into the
Okay, yeah,
that's not the discussion. Yeah. Right. So the first and I think most important, well, one of the important problems we have with the current implementation EAS, what I think is an important one, given the feedback we have on the list, is how we interface EAS with the rest of the kernel. So should we rely on this subsystem or this subsystem? How should we factorize code with schedule like that? The proposal made so far is to have a code architecture like this. So we have other suggestions, but the current proposal is the following. The idea would be to have like PMOPD framework as an abstraction layer that will like we will like have the power values propagated up to the scheduler through the OPP PMOPP layer in order to have a common energy model loading code from the scheduler. So this energy.cpy will be in the kernel shared directory will be common to all users of EAS. And then this file just will have to call the OPP framework in order to get power of the OPPs. And then build data structures that will be used by scheduler and Perret. So this works fairly okay for ARM and ARM64 platforms, but there is, I guess, a question mark for this part is how acceptable it is to actually rely on the OPP framework for other architectures. Let's say if x86 wanted to use EAS at some point, is it acceptable or not to
well, if you won't work. It's not a matter of acceptable or not. Just it's not doable.
Right.
So,
okay,
so this is right.
So if we have to change this, one of the suggestions on the list was to use CPU instead or schedule.
It was more that the there are two places with the standard energy model. There are two or even three places where the same information is used, because the CPU freak uses this information, your EAS will use it, and then the thermal subsystem uses it.
Yeah.
Yeah.
And so it would be good to have a common data structure for all of them to look at, just to get the information from there. And the data structure should not be PMOPP, because there are systems where it is not existing even. So you need to have something that can be used on all the architectures, ideally.
So the question of the, so I agree with the point, like at least on scheduler sample, for example, it's not very short. Then there's on ARM, like the aggregation between the CMI and DT and things like that. Maybe it will become table. This is first. But I guess that becomes
yeah, but it would, if you had the more like abstract data structure, then it may make more sense to actually populate it directly from a CMI instead of going through PMOPP, as a middle man in the middle sort of, and then
so CMI also talks about abstract levels. The
right.
difference between CMI and CMI does have the notion that there might be an interface level.
The reason I want to have like kind of common ground for CMI and DT and whatever is that the computation for when you have DT-based power estimate, you have some computation needs to be done. So
Oh yeah, sure, but then
today this is done in
but
thermal subsystems,
then
so you
it
have
is
to do
going to be
somewhere.
static data anyway, right? Because the T doesn't change.
Yes.
Right. So you can just pre-compute those numbers and put them somewhere.
You have to know the OTP. And
okay, but
necessarily know them
still.
before you do it.
And
that's for the case where you have the DT and you.
Yeah, yeah.
But you have, I mean, the point if you want to generalize for other users, then you have to make it in a way that is reusable as you think.
Yes, I agree. But, well, I mean, I get discussion for CMD from CMI and DT because it's a non-specific kind of issue.
Yeah, yeah.
But then for the shading standpoint, there's another possibility. So one idea maybe will be to use the CPU frequency table as some kind of data structure that could be read by multiple clients across the schedule. That mean that
except that in some systems that doesn't exist either. So I mean, it's not like you can use it everywhere.
If you don't have CPU free, probably don't want to use it.
No, you have CPU free, but you don't have a frequency table, like if you use CPPC, for example.
Yeah.
Pretty much.
Also, you might be still wanting to use the information from schedule or thermos, even if you're not using EAS.
Yeah.
So is there a place we can take a table like this as you come up with a new framework where you can describe an energy model, which is in that sounds like that's what we want. So one place to store it, and then we can have multiple frameworks that can actually populate. It can come from
well, it does make sense to do it because of so you have multiple sources of possible sources of information, which can be different, like the DT, CMI, like CPPC, whatever, And then you have to have a common representation of that so that the scheduler can use it. And ideally, CPU Freak could use it too, because then it is a common representation. Why not?
Yeah.
And then the thermal subsystem could use it too, because it is a common representation.
Yes.
So why don't we go for that?
Yeah, that seems sufficient. And if we create yet another framework.
Well, it may, or it may at least create another data structure, thing, because it may be, you can call it a framework because it's data structure plus a way to populate it, right?
Yeah, no way.
But and then the way to access, but accessing should be just, accessing memory, like, walking something, like a table or a tree or something.
Yeah.
I mean, it makes sense to have another framework. You have multiple clients, then.
Yeah, I mean, I'm not against it.
So because of efficiency reasons, that has to be accessible as, through walking memory rather than using accessor functions or something like that, because that otherwise you'll have overhead, which may not be acceptable, like in FastPass.
Maybe one of the arguments why we call it framework is even just deciding where the calculation model has to be. It can be issued with where it has to be like energy to see which is under shaded, is under responsibility of someone to maintain. So there is these viewpoints and other frameworks have to access data structures that are under shaded.
Generally, you need to know what the available states are and what the cost of them is, and that can be, well, in the case of things like CPPC, it's sort of tricky because the number of states is big. Like, it may be like, but still it is not a huge number. It's like 255 at most, I think, per CPU.
But you could also go to a point where you just have some selected points. I mean, if your curve is...
You can use fewer of them. You don't have to use all of them. But what I was trying to say was that the number of states may be like in the hundreds sometimes. But this still is not a huge number, I think.
Also,
You can choose a few points.
Yeah, I think if you have 10 points for a CPU,
actually 5 is okay, as far as I can say, because from experience.
the non-linear impact point.
You
picture is like 3.5.
The curve is like this usually. So 5.
And to be honest, if you start to see more of the side of things.
Yep.
Now you just populate. Then this is what I'm saying.
Yeah, so I guess the idea we had at the beginning was to say this is a OPP based touchdown, so just like practice it somewhere. Right, we have OPP there.
But that means we should design it as general that also like the thermal subsystems can use it. Because I think thermal right now they are
Yeah, so the idea is that generally speaking, if you have it's better to have one source of information that multiple places can use. Because then if you have two sources of that information and they don't agree with each other, then you have a problem because then you don't know which one to use, right? Because this tells you that and that's
true. The thermal, if it's currently tied to P and OPP, it can only be ARM. And I think one of the Intel guys was looking at GPU, CPU, thermal things as well.
Yeah. So the people are looking at that, and so if we can. Great. So in principle, we could also use this with HWP systems because then you can just use a few, like points on the curve, and then say these are the states that we care about essentially, right? And then set the EPP to those values, for example.
Yeah, I guess.
Yeah. But this is too specific for me, right?
Yeah.
Because this is
still.
yeah,
you can.
In other design,
also don't make it too complicated. Just to have a weird thingy and some inline methods. Don't make a big C compilation thing. Maybe just to populate, but we want the access and traversal of this to be as direct and immediate as possible.
Yeah.
For performance reasons in EAS.
So even for populating doesn't need to be all complicated.
It doesn't have to be, but even if it is complicated to populate it, then we don't care because this is only done once.
Yeah.
Or once in a blue moon.
Yeah.
And but the traversing has to be very, very cost efficient.
Yeah. So there's just one last thing. There were also discussions on this about trying to factorize code between EAS and schedule developments. And if like the data is used by schedule, so frequency is different from the power values of factorization for that's also one of the reasons why I want to stick at these frequencies. Because like schedule.
So the idea is, I think, that for the systems that have a frequency table, the points in the frequency table would match whatever this data structure has. There would be a one-to-one correspondence.
So where I didn't follow, in which case you would be the OPP table would be matching different values?
I mean, schedules or right when you in Dietmar schedule or like try to find the frequency of which sense frequency you want to select. You don't look into right, just look into
yeah, but you can populate both at the same time with the same values. So,
yeah.
Right.
But maybe another problem that you are thinking about is that we have some policies within Game Extract that are the margin, whatever, and that's specific for schedule field, and maybe is aligned with other usages, or maybe the shifter or the temp, for whatever reason. So there is a need to have a unified policy on to identify how we work the table.
So actually, the schedule governor doesn't even use. Yeah, if there is a frequency table, it will look at it. But then
that's in the driver.
Yeah, but if there is none, the driver will just select the frequency, and the schedule doesn't even know.
The schedule doesn't do anything. So we leave all of that to the CPU.
To the CPU framework, I think. So the
There's a table to look up in the table. If we have the power values in that table, then we could use in EAS that look up.
oh yeah, I know, but then the point here is that the schedule governor doesn't look at the table by itself, but it asks the CPU freq subsystem for the available frequencies anyway. And that has to be done this way because there are no frequency tables on certain architectures at all. So yeah, so CPU freq as a framework has owns this information today, but if you can have a common data structure, then it could access it if it's available. Just instead of looking into the frequency table.
The driver could look into this table instead of its own table. Right.
Or the CPU freq framework itself. I mean, the core could just look, because what happens now is the driver provides a frequency table, and then when it is present, the core looks into it and doesn't ask even about everything. Right. So it could, instead of looking into the frequency table, it could look into the common data structure that the EAS would be using, if that's present, right? And then look at the frequency table and then do something else. So that's
like some kind of flag.
No, it's just this is populated, and you know that it is.
I mean, you know where to go, right?
Yeah, no. So if the EAS data structure is populated, and you will know that the values make sense, right, in it. And if it is not populated, then you don't have anything to look into. So this is not a problem. Yeah.
Basically a fallback.
Just a fallback. Yeah. If this is present, look into this. If not, then look into the other thing. If not, do something else, and so on.
We should just give up the idea to squeeze EAS into free. This is what I get here.
Yeah, that's no. So nobody has been proposing this.
As long as we agree that we have to come up with this new data structure and possibly CPU freq can use it, and also thermal later.
I mean, you have
That's the way to
multiple
go.
users, so it does make sense to have a common thing.
This is like a nice design to see.
Yeah.
Okay. Cool. 10 minutes. Wow. So this is the second problem we have with EAS. EAS relies on the fact that individual CPUs, like you see here, they are not essentially overutilized. Overutilized means there's so much going on the CPU that the tasks essentially on the CPU they exceed the capacity of the CPU. So that's why for utilization of the existing CFS scheduler we have this capacity margin, which means 80% of the capacity of the CPU, and then we would say a system is, or in this case, the system is the CPU is overutilized. And when this happens, we can't essentially place tasks in an energy-aware fashion. When we think about like a check domain hierarchy on this system, which is exactly the system we had before, the IP 960, 3 little CPUs, 4 little CPUs, 4 big CPUs. This is the check domain viewpoint of CPU 0, which is a small CPU. In this case, we have the frequency domains per cluster. And the current implementation of overutilization is following this hierarchical approach, where we use the shared SD data structure. You have to see that each of those CPUs, they have per CPU data structure. So this we have essentially on this level for those 4 little CPUs, we have 4 chat domains here, and they all share a chat domain where we can store common data between those 4 viewpoints. And the overutilization is currently implemented here. So if you detect during the scheduler operation that one of those CPUs is overutilized, we would set the overutilized flag here, and we would essentially bail out of the select task run queue pair to eventually go into select either sibling or even to the slow path. And the current implementation is like this. We have this implemented on all levels. So in select task run queue fair, the first decision we make, can we do energy aware scheduling? We would, when the task wakes up P, we would essentially check this check domain or this one here in this case. If we are over to this, we would essentially bail out and go into the pass path. This is helpful for something like Hackbench, where we don't want to pay the extra the amount of compute. We just want to go select idle sibling. When we go, if this is not the case, so we could essentially wake up energy aware. We would try to figure out what's this for each domain that's existing code, by the way, and we go up towards the check domain, which is still not overutilized in this case. So we can iterate over all 4 little CPUs and all 4 big CPUs, and do this fine energy aware scheduling. Overutilization means if the system is not overutilized, we would essentially don't have any load balance going on in the system, because the load balancer which essentially just balance the load, something we don't really want to do in energy aware scheduling. Currently, we are not really sure if this hierarchical approach actually makes really sense. Because what we really want to do is something like also in select idle sibling, where we know already that we are interested in a certain level in the system, where we see CPUs of different CPU capacity. So even though here energy aware scheduling could make sense, what we really want to do if we want to save energy is to force a little task onto this, and even if the correct CPU of the little task would be a big CPU, we would like to force on the little CPU. So we have to do energy aware scheduling anyway on this level, where we have the SD asymmetric CPU capacity flag set. So an alternative would be to just say we always want to check if this level is not overutilized, and not do this like starting from the bottom of the schedule. So currently it's implemented like this, but I think this way would be more in line with the energy aware scheduling approach anyway, because we different CPUs on this.
Okay. That makes more sense. Okay.
So in Android we have this right now, where we declare a system as the boundary, and on CPUs where we care about, like we have 8 logical CPUs or maximum 8 that, so we could essentially, this is the check domain die level is exactly the same system.
Yeah, it comes down to the same until somebody builds a multi-socket big little thing. Which I'm sure somebody someday will do, and some idiot will.
Well, but not anytime soon. Okay. So I have no opinion.
Can I make a point? So I was going to say one of the drawbacks of the system-wide thing, doing it from the top, is like if any CPU goes above the tipping point, then the whole system would be like in this overutilized state, right? But it's not really overutilized, like the other CPUs idle.
But the algorithm would essentially try to iterate over all CPUs. If one is overutilized, then you can't really make a
The regular load balancer will, if it is on very low, that's very good.
And so if you have just like, let's say, big neutral, where we have like just little CPUs, but also there's another. If you have just the little one without another one, little ones on those side, not the big one, then you will quickly balance that by upgrading them. So this is the equivalent. Yeah. If you have the big CPUs with also not the little ones, then you could maybe do another replacement on the little side. But at the same time, if you are otherwise on the big side, that means that your big CPUs are consuming power as crazy, as massively. Even are you really going to save anything by doing that? Placing the little side? Yeah. One thing was about the complexity of the algorithm. So just to make it very simple, well, I don't have to go through all of this, but we sort of talked about that in the beginning. The idea of the algorithm that we have today is basically we define in each frequency domain which is the CPU that has the max band cap, and this one will be our candidate in that frequency domain. So we'll say let's start this one and the energy plus there, and this one computes the energy plus there. And we end up with a complexity of the algorithm, which is the bigger complexity is something like Mn, where M is the number of frequency domains and N is the number of CPUs, right? And yeah.
A question.
Yeah.
Is there a way to just compute the delta between the current energy and the and a new one, possibly?
That will be the right thing to do indeed, right? Especially if you end up with a system.
Because
Peter is point
without idle states.
Sorry?
Without idle states in the picture, it seems like you should be able to compute the delta.
Probably, yes. Like it would be especially nice maybe if you have like this CPU DBFS thing, because in that case you end up with n square complexity, which is horrible.
Right.
But if we want to do that, so I guess the question is it really well, I guess the question depends on the code, but I have a feeling that doing a delta thing or caching the values as we go or something like that will make the algorithm a lot more complex. And given the fact that as of today, the only platforms that will use this thing are digital systems for which we have only 2 frequency domains.
And there's no longer
is it worth it? I mean, having the complex algorithm for the first step.
Well, okay,
so what I said is I'm fine with it being O squared for now. Just put in a big comment that yes, it is O squared.
Right. Yeah. And then we can improve that. But there is room for improvement.
Maybe put in a warning in the initialization code when FM gets bigger than 4. Who knows?
These things.
Because then people will get a warning when they do build a funny system that they really rather might want to look at fixing this.
Yeah.
And that's particularly helpful when you're putting things on the market and you see, hey, my schedule is using something which is O squared, and it's good to have a big fat warning over there.
Right.
So warning is fine, or shouldn't just be allowed in those cases.
Or both.
Or both.
Yeah.
Okay. So,
okay, the last point is not very important.
Right. Thank you.
Okay, cool.